Hey everybody, I'm so excited about today's lesson. We're going to be learning about logs or logarithms. And in order to understand logarithms, we first have to have a conversation about our inverses. So I want you to go ahead and take a look at these. And again, if you were able to print out the notes, great. And if you weren't, that's okay. You can just follow along on notebook paper. So every function has an inverse, and we find the inverse, remember, by swapping our x and y and then solving for the new y. So I want you to check out this graph over here. If I have this linear function of y is equal to 2x plus 6, that's going to be this value here, and I'll go ahead and get my straight edge. So I know that this is this linear equation because I can see it has a slope of 2 and an intercept of 6. So here's this graph here, this equation in purple. When I want to find the inverse, what I do is I switch my x and my y. So I put my x in my y position and my y in my x position, and then I go ahead and I solve for the new y. So this is what I want to solve for. So I'm going to subtract 6 from each side. And then when I divide by 2, I get 1/2 of x minus 3 is equal to y. And if you look here, you can see where this blue line is. This is the linear equation that represents this new equation that I got when I swapped my x and y and then solved. So the cool thing about inverses is that we first of all know that they are a reflection on this line, y is equal to x. And if you look here, you can see this line here, y is equal to x, is that line of reflection between my blue and my purple line. And we did this with not just linear, but also quadratic functions too. So if you look here, I have a quadratic equation. I know it's quadratic because of that squared. So I can look at this parabola that represents its graph here, and I know that that's an x squared. It doesn't go left or right. You notice there's no h inside of the x term moving it left or right, but there is this vertical shift up 4. Now again, I have my line of reflection as my parent function, y is equal to x. But what's interesting is when you look at the graph of this reflection, I can see, but what the heck is going on here? And this becomes an interesting conversation about how come when I have my inverse, I don't have this negative output. So if we go ahead and solve this inverse, I go ahead and I switch my x and y again, and then I'm going to solve for my new y. So I'm going to subtract 4 from each side, and then of course I take the square root. And when I talk about the square root, am I talking about being able to have that negative output? So it's an interesting conversation. If I talk about my plus or minus, I can have that part underneath. But when we look at what's happening, we end up knowing that when we go to take the square root, we can't take the square root of a negative number. And that's what ends up creating just this positive inverse. Okay, so stick with me, because now we're going to go ahead and approach the conversation of exponential functions. So exponential functions, you remember, is where I have my x is up in the exponent, my output is the result of my function, and it's this base to whatever power. So if it's easier for you to have an example, you can go ahead and think about y is equal to, I don't know, let's go ahead and have 3 squared. So when we go to switch our x and our y, or we can talk about, leave that being x, when we switch our x and our y, we end up with having x is equal to 3 to the y. Well, again, my job is to isolate this y. How do I get that y isolated? And mathematicians spend a very, very long time thinking about and wondering about this. In fact, the whole reason that we ended up with that variable up in our exponent is, remember when we talked about them trying to come up with ways of maximizing their money for our interest formula, and they wanted to solve for time. They wanted to solve for any time that x, or that unknown value, is up in the exponent position. It puts us in a curious thing of how do I go about and solve these. So if you look at these next ones, some of these we just know with our friendly numbers. So if I wanted to go ahead and ask you, just using our friendly numbers, 3 to what power is equal to 9? Well, if I ask you to fill in that box, like 3 to what power gives me an output of 9, you know that that's 3 squared is 9. But how can you solve for that x? Okay, let's talk about this one. 5 to what power is equal to 125? So having that unknown up in the exponent position creates a little bit of drama. So if you wanted to, you can go ahead and get your graphing calculator, and if you wanted to, you could go to your function screen and go ahead and say 5 to the x power, and then you could go ahead to the table and say, oh, here's 125. I see that. So when x is equal to 3, that's 5 to the third power. So our calculator can help us when the numbers are friendly. And remember, that's a big when the numbers are friendly, because they're not always. Okay, so 2 to the what? 2 to what power is going to give me 32. Again, if you're good with your powers of 2, you know that if x has a value of 5, then 2 to the 5th is 32. So here's a curious part, and this is where the calculator might not always help us. By the way, if you're wondering about that 2, 1, here is 2 to the 5th is 32. All right, let's follow that same pattern and go ahead and come over here and say, okay, what is 16 to the x? And if I go to my table of values, notice I don't see an output of 4. 16 to the 0 is 1. 16 to the first power is 16. 16 squared is 256. But the problem is I'm looking for an output that is smaller. So you guessed it. Do we go up? Maybe not. What is the relationship between 16 and 4? Now you know that the square root of 16 is equal to 4. So what does that square root look like? Yep, you got it. 16 to the 1/2 power. That's going to be the square root of 16. So don't forget, your exponents can most definitely be radicals also, if I'm taking the square root or the third root or the fourth root by having that radical rewritten in exponent form. All right, one more tricky one for you. So 3 to the what is 1/9. So we talked about fractional exponents, but now what other kind of exponent? What's going to make this 3 move down to the denominator? Yep, you guessed it. So if I have 3 to the what power is equal to 1/9, I know that that's 3 to the negative second is going to give me 1/9. Okay, so here's the deal. You're now sitting there thinking, okay, you do all those, but maybe I didn't. So what we need is a plan for maybe when things are not quite so friendly. So mathematicians made up something called a logarithm, or for short, we call it logs. And here's the rule. If I have b to the y is equal to x, I can rewrite that as the log base b of x is equal to y. And the kicker here is I want you to think about, we're always solving for our exponent. So you want to give yourself a note that you are always solving for the exponent. Okay, so we read this, the log with a base of b of x is y. The base of a log is never negative or zero, and we can see that up here when we look at our inverses. We can get an idea of why that might be a reasoning. If I were to think about a graph of an exponential function, I know right away that that exponential function approaches zero but doesn't ever reach it, right? And it doesn't go into the negative. So when we're talking about the base of that log, we're never going to have that happen where it is negative or zero. I'll be able to take the opposite of it, but it won't have a negative value. All right, so let's practice rewriting, because if you can give yourself one steady example that you can go back to and think about every time, it'll definitely help you. So with me, I always like to, if I think about what 3 squared is equal to 9, the log is an exponent. So you're asking yourself, so the log that is of this base that gives you this outcome is equal to what? So you're always asking yourself, what is the exponent? And this exponent here is what it is we're solving for. All right, so we're going to have some practice ones. And here we go. You guys know how this works. If you follow along with me and copy my work, chances are you're not going to know how to do it in the future. So you have to do your best at doing your own work. So let's take a look at this one. I'm going to write the word log. And really all I'm doing is rewriting. I'm not taking the inverse. Inverse and exponential equations are inverses of each other. I am rewriting. I don't have an x, I don't have a y. I'm coming up with another way of saying this same thing, but instead of solving for the value of my function, I'm going to be solving for the exponent. I'm going to be able solving for the exponent. I'm going to be solving for the exponent. So the kicker here is, remember, your exponent is always the output of a log function. Your base, I want you to imagine somebody saying, what are you taking? The log of what? The log of base 2, the log of base 3, the log of base e. Okay? This value is what this whole story gave you. So if I had this base to some mysterious exponent, what value do I get? I got 16 as an output. I got 1/9 as an output, and I got 1 as an output. So you're asking yourself what exponent is going to give me this value for this base? What exponent is going to give me this value for this base? If I have this base, to what power, here is my outcome. So it's real important that you pay attention to it. A lot of times on the top of my paper, I'll go ahead and give myself 1 as an example so I can make sure I can follow the pattern. All right, so when we look at, we have 2 kinds of logs, and our natural log that has a base of e is written as ln. So ln is your natural log. You know where that is. It's on the calculator, and you've seen that button there, and you've wondered, what is that button for? That's your natural log. Your common log is a base of 10, and it is written as just a log. You don't need to write anything down in the bottom with it, because everybody knows when you see the word log with nothing after it, can you see on the calculator? When you see the word log with nothing after it, then they're talking about base 10. So I have base E for ln, that's my natural log, and my log is base 10. One of my kids one time said they remembered that the O in log is like the O in the 10, so that's how they remembered which one was which. Okay, so here's this next thing. It says switch the log into an exponential equation. So here is going to be the opposite of what we did over here. Here we went from exponent to log. Now I want to go from log to exponent. So you pause the video, see if you can do this, and come back and see if your answers are right. So no cheating. Make sure that you pause. Go ahead. Okay, how'd you do? So when you're looking here, the base is that little itty bitty number. So the base to this power gives you this result. The base to this power gives you this result. And here what's interesting is we don't know, it doesn't say. So whenever you don't know or it doesn't have the base, but it has this word log, you can assume that that is a base of 10. And remember, here's your exponent and then your value. So here we're just rewriting. We're going back and forth between exponential expression and the logarithmic expression of the same equation. Okay, so I got a little carried away and I kept going while I was doing my key. So I have my calculator covering up those answers. But our next part is when we have the word evaluate, that means that we're trying to figure out what the value of this is. So you want to say, okay, well, what exponent on this base gives me 32? So when we're evaluating, you're coming up with the value. That's that key word that you always want to see when you have evaluate. What is the value? So what exponent on the base of 2 gives you 32? What exponent on 3 gives you 9? And what exponent, careful here, remember we have a log base 10. What exponent on 10 gives you this output of 10? So go ahead and pause the video and see if you can fill in those boxes. And then you can come back and check your answers. How did you do? Because I know 2 to the 5th, so 5 goes in there. The log of the base 3 that gives you 9 is 2. 3 squared is equal to 9. The log, the exponent, and every time you say the log, you can substitute the phrase the exponent on 10, because remember that's understood to be there. The log, the exponent on 10 that gives you 10 is going to be 1. 10 to the first is 1. Okay. So of course we can do all this on the calculator too. It's kind of like your math facts. You want to be able to have your friendly numbers in the front of your brain, but you also want a resource for where to go. So your Desmos or TI calculator tips work like this. Let's talk about the TI first. Here's my log and ln buttons. I don't know if you can see them because the calculator is black. But my log is going to be when I have a base of 10. And this ln is my base of E. On the Desmos, when you go to, and you have to find this functions key. You have to click on this functions key. And then you have to arrow over to miscellaneous. And when you get there, you can see right here, here's your base of E, and here's your base of 10. Okay, so when you have the log button is for base 10, and the ln button assumes a base of E. Now here's something you need to know. 10 is not always our base. So we have a base 10 number system, but that's not what we're talking about. So if we have something other than a base of 10, you're going to use this key here, And this key allows you to fill in what your base is. So if it's base 10, if it's base E, or if it's something other than, you can go ahead and look here. And in fact, if you go up to these other answers, here's a base of 3, there's a base of 2. If I wanted to calculate them using Desmos, I would have to use this button here. Okay, so the calculator is not so simple. We have two different options, and it all depends on whether you have a newer or an older model. If you have the newer model, then it's easy. You have to go to the Math menu, and you're scrolling down past 10. You would think it would be called 11, but instead it goes to A, and they say log base. And that, again, is going to give you a code where you enter in what it is that you're looking for with the base and the value. If you have a model of the TI that is older, then it doesn't have this. When you go to Math and you scroll down, you're not going to see it. So what you have to do is you have to change it into a base 10, and you can see you have to change it into a base 10 formula. So you're going to take the log of the value over the log of the base. So it's log base 10 of my value and log base 10 of my original base here. I always remember this because the base goes to the bottom in my change of base formula. All right, this makes so much more sense when you see us do them. So again, if you're able to print out the page, awesome. If not, you can be using a notebook paper, and then you could go ahead and figure out what these values are. Now, you always want to use your brain. So if you have the ability to calculate these without the calculator, then go ahead, do it. Maybe you want to say, okay, 10 to the what power is equal to 25. Guess what, friends? That's not a friendly number, but it is a base 10. So I can go to my calculator and I can say, okay, what is the log of 25? And it's going to give me that crazy answer, 1.3, blah, 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 blah. Okay, and for our purposes, we're always going to round to the nearest hundredth. So we're going to have is equal to 1.39 rounds up to 1.40. So here's the thing. As with all things in mathematics, we should be able to test to see if we got the same value. So when I go ahead and I say 10 to the, if I go ahead and retype this number, 1.39794, good enough, notice I get pretty darn close to 25. So what I ask the calculator for is, hey, what's the exponent that goes to 10 to give me a result of 25? It says 10 to this power is going to give you 25. All right, let's take a look at our next one. Our natural log that gives me 3. Here's what I'm asking the calculator. I'm asking the calculator, hey, what exponent goes on top of E that gives me an output of 3? So again, I'll go to my graphing calculator and I'll go ahead, see this LN button there? When I do that, see how I get the natural log? So I want to know, what is the natural log of 3? 1.09. So I have 1.0, oops, when I want to round up, we're going to call it 1.10. And again, I can test because I can say, okay, E to the 1.0986122289, and then if you'll notice, that's pretty darn close to 3. Okay, so that was, this is too hard to read, 1.10. Okay, so when we have a exponent that gives us a negative output? Let's think about that. So if I have an exponential graph, it looks like that, true? Do I ever have a negative output? So this calculator, I'm asking the calculator what exponent goes on 10, because remember it's log base 10, that's going to give me an output of -2. And I got to tell you something, I'm already suspicious of this one not working out. So we'll go ahead and say, go ahead, what is the log of -2? Notice I get a non-real answer. I get something that doesn't work. So what we're going to say is this is undefined, that there's no real solution. No real answer, no real solution. All right. If I have the natural log that goes on e, so that means that e to what power is going to give me a 10. So if I go ahead and take the natural log of 10, 2.3 is equal to 2.3. All right, let's keep moving. Here I have the log base 3 of 12. Now notice in all of these examples, I have a base. So my calculator is an older one. I don't have the ability to do it the shortcut way unless I go get this calculator, which is the newer one. So I'm going to show it to you both ways. I'm going to take the log base 10 of 12 over the log base 10 of 3. So this is my change of base formula. Change of base formula, where I go ahead and I take the log of the base, that one goes to the bottom, and I take the log, I'm looking for the, and remember, every time I say the log, I'm saying the word exponent. So I'm asking myself 10 to the what power 12 over 10 to the what power is equal to 3, and my job is to figure out what goes in these boxes. So when I go to my calculator, I can say, all right, I have the log of 12, close parens, divided by the log of 3. And my answer is 2.26. So if I go get my newer calculator, and you can see I'm already set up where I have that. I'll show you where I got that from. If you go to math and then you scroll all the way down, and it should be named 11, 6, 7, 8, 9, 10, 11. Nope. It goes to A. That's your log base. So you choose that, and I put a 3 in there, and I'm going to use my arrows to go over here. And you can see I got the same exact number. So whether I use my change of base formula or whether I use my newer calculator, then I can get that same answer. We like kids to still know this, so regardless of what calculator they have, everybody can still find the right answer. Now Desmos is just as simple, where you just type in log, and you'll choose to put the 6 down low. Okay, so I'm going to keep doing it the hard way. I'm going to keep using the change of base formula so you can see what it is. So I'm asking you, let's see, we'll do blue. So the log base 10 of 0.5 over the log base 10 of 6. I'll go to my calculator and say, okay, what is the log? Base 10 is implied of 0.5 divided by the log, base 10 is implied, of 6. And then that'll give me negative. Now, we talked about how your value here can't be negative, but your exponent can. Because remember, we're solving for what exponents make this happen. And this definitely makes sense to us. Oops, I want to round. Keep getting caught on that round. Because if I want to know what exponent goes on 6 to give me a decimal, of course it's going to be division. Remember, negative exponents are the same as division. So if I have 6 to the negative 0.39 power, of course that's going to give me very close to 0.5. All right. So the log base 8 that gives you an output of -1. Anybody suspicious of this one? So can we have a negative exponent? Yes. Can I have a negative output? If you go back up to my graph, is there ever a time that an exponential graph without a transformation gives you a negative output? I'm thinking not. But we'll go ahead and we'll try it. So we'll have the log, we'll have the log base 10 of -1 divided by the log base 10 of 8. And you know it's going to give me an error. So we're going to call it undefined or no real solution, no real answer. All right. When we have the log base 2, that gives me 78. I'm going to take the log base 10, that gives me, 78, and I'm going to divide that by the log base 2, or base 10 of 2. And that's going to be 6.29. And again, don't be afraid to always check and see your solutions, because this means that 2 to this power is going to give you 78. 6.2. Now you can see I rounded up to 9, but the more decimals that you type in, the more accurate your answer, and you're going to get pretty darn close to 78 there. Pretty cool, right? Okay, so here's our important observation. You cannot take the log of, first of all, you cannot take the log of 0, because you're never going to have 0 as an output. Again, check it out, right? Or a negative number. Okay, and this big question is why? Okay, why not? Because remember, the log is the exponent, and then we're going to have that value or your output of that function is not ever negative as an exponent equation. Okay, so when you go back up and you look at this graph, it becomes important to know what an exponential graph looks like and why those things happen when we're calculating it versus what the graphs of it look like. Okay, so logs are important for many reasons. In fact, when we were solving for this on one of our application problems, we went to the calculator. And now we know if we need to solve for that exponent, we can use a log instead of guessing and checking through the calculator. Okay, and that goes back to mathematicians created logs because they were inverses. They needed an inverse of an exponential equation. Okay, our next lesson we're going to talk about graphing logs. That's going to be next week. Okay. So if we find the inverse of the following functions, now is when we start using the inverse. We can say the log base 3 that gives the result of x is equal to y. When you want to find the inverse, remember, you switch your x and y. Okay? So now what I see is I know that 3 to the x is equal to y. And that's going to be our inverse. So if I have y is equal to the log of x, that means that I'm going to switch my x and my y. And that means that 10 to the x is equal to y. And you're like, wait, where'd she get 10 from? Because it's a log, it's a common log that has 10. It doesn't have a base written down, so I knew it had to be 10. Okay, next comes ln. When I switch my x and y, my x goes here and my y goes here. So if I want to switch from a logarithmic expression to a exponential expression, remember I know this is base e, that means e to the x is equal to y. This and this are inverses of each other. So remember with inverses, step 1, you switch x and y, and number 2, you solve for your new y. And the graphs of those two equations, if I were to graph both of these equations, I would see that they are inverses. In fact, I don't mind doing that. Let's take the time to go ahead and say, okay, if I wanted to know y is equal to the log of x, and I wanted to know where I have y is equal to 10 to the x, when I go and look at my graph, I can see that these equations, and I'm going to go ahead and zoom out so you can get a better look, but I can see that here's my y is equal to x function, and you can see that this exponential function and this logarithmic function are inverses of each other. Two separate equations. Okay, let's finish up looking at 4 and 5 and 6. They're asking us to find the inverse. So that means I swap my x and my y, and then I have to solve for y. Step 1, swap. Step 2, solve. So the only way to solve for a value in an exponential position is to take the log of it. So I know that the log base 2, remember that's my exponent, right? That gives me x as a value is equal to y. When I swap my x and y, the only way to get this y, the only way to solve for it, get it by itself on one side of the equal sign, is saying this exponent is going to be equal to the log of this base that gives you this value. So whether you have your y as an output or whether you start with that output value, it doesn't matter. Here we go. Guess what? When we have e, we can go ahead and use the natural log. In fact, here we missed it. We have the common log here. So we can say y is equal to the log of x and simplify it and not write that in base 10. We can do the same thing here. Swap your x and y. So I mean my exponent is equal to, and I can say the log, and I could say base e that gives you x, but this is something we don't ever write. We simplify that. So y is equal to the natural log of x. All right. So good job. And have some fun with these exponents this week. I'm going to have one more practice. But thanks for tuning in. Bye.